Now let's take a look at some generic interpretations of the second order partial derivatives. Now the direct interpretation can be made when the first and second order partial derivatives all have the same variable. In other words, they're not mixed. We won't have an x and a y. The interpretation is the same with first and second derivatives of one input variable. Remember, first derivatives are the velocity, second derivatives are like the acceleration. We need to compare the signs of both the first order partial derivative and the second order partial derivative to determine if the function itself is increasing or decreasing, and if that change is slowing down or speeding up. Again, velocity and acceleration. So let's look at how we would interpret it if they both have the same sign. So the changes occur at an increasing rate. For example, if our first order partial derivative is positive and our second order partial derivative is also positive, that means f is increasing at an increasing rate in the a direction. In other words, all of the other variables still remain constant. If the first order is negative and the second order is also negative, f is decreasing, but at an increasing rate in the a direction. So again, if the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. But if the first and second orders have the same sign, then that increasing and decreasing is occurring at an increasing rate. What if they have opposite signs? Well, then the changes occur at a decreasing rate. So if the first order derivative is positive, f is increasing. But because the second order partial derivative has the opposite sign, in other words, it's negative, then f is increasing at a decreasing rate in the a direction. If the first order derivative is negative, then f is decreasing at a decreasing rate in the a direction. Again, first derivative is positive, we're increasing. First derivative is negative, we're decreasing. But if the second order partial derivative has an opposite sign, then those changes are occurring at a decreasing rate. Just so you know, these will help us find maximums, minimums, and saddle points later on. So let's just do some more examples. In example F, we are asked to find the first derivative with respect to y. The chain rule still applies. Since it is e, we keep e as it is, and then we multiply it by the derivative of its exponent with respect to y would just be -5. So this would give us a -75e to the 3x minus 5y. Again, the chain rule still applies. In example G, we'll take the first order derivative with respect to x of a rational equation. Remember our low d high minus the high d low over the low squared. So we take our denominator, 4x squared plus y to the 5th, times the derivative of the top with respect to x would give us just 6x, minus the top, 3x squared minus 2y cubed, times the derivative of the bottom with respect to x, which is 8x, all divided by the bottom squared. The quantity 4x squared plus y to the 5th squared. Now we can simplify the top. I would leave the bottom squared. We distribute, giving us 24x cubed plus 6x y to the 5th. Again, we're distributing the 8x over here, but it is with a negative, so signs are going to change. We get a -24x cubed. -2 times 8 will give us a -16, but again, we're distributing that negative so that negative 16 will become a positive 16xy cubed, all divided by our denominator squared. I realized I am writing all of these as if it's a function and not a partial derivative. That was a little misleading there. We combine like terms. We end up with a numerator of 6xy to the fifth plus 16xy cubed divided by 4x squared plus y to the fifth quantity squared.